Hello and welcome back to Educator.com and welcome back to physical chemistry. So we are going to continue our discussion of molecular spectroscopy. Let's jump right on in. Okay, now we started our discussion of molecular spectroscopy by talking about vibration rotation transitions. And we said that a transition in the vibrational when molecules absorb infrared, they're going to make a vibrational transition. And with those vibrational transitions, you get accompanying rotational transitions. Well, if you stay in the microwave range, we actually can just stay in the pure rotational state. So that's what we're going to investigate today, pure rotational spectra, not the vibration rotation spectra that we did in the previous two lessons. Okay, so if we stay in the microwave region, let me go to, you know what, I think today I'll do it in black. So if we stay in the microwave region, we can get a pure rotational spectrum. And again, remember what we said, for a pure rotational spectrum, there are some selection rules. The delta J equals plus or minus 1. But what's more important than that is this existence of a permanent dipole. If a molecule doesn't have a permanent dipole, like N2 or O2 or something like that, it's not going to be, we're not going to see an infrared spectrum for it. So there needs to be a permanent dipole in order for us to actually see some microwave activity. Okay, so if we stay in the microwave region, we can get a pure rotational spectrum. All right, so it's always good to review the equations over and over and over again. So we had that the energy is equal to, we said, h bar squared over 2I times j plus 1, where j took on the values 0, 1, 2, and so forth. We said that I was equal to the rotational inertia, or the moment of inertia, mr squared. And we said that the degeneracy of these rotational states is 2j plus 1. Now, in terms of inverse centimeters, which is really what we're going to be dealing with and what we've been dealing with, in terms of inverse centimeters, wave numbers, we had this rotational term, f of j, was equal to this b tilde times j plus 1. J times j plus 1, where b tilde, we said, was Planck's constant divided by 8 pi squared c I. Now, as we said before, the selection rules for rotation, remember, we're just talking about pure rotation now. We have to have delta J equals plus or minus 1, one quantum state at a time, and a permanent dipole in the molecule. Permanent dipole. So the frequencies that we observe in the rotational spectrum are, or that we should observe, are, of course, the upper minus the lower. So it's going to be f of j plus 1 minus f of j. Well, f of j plus 1, put it in here. J plus 1, just put j plus 1, j plus 2, put it in here. Should I do the, you know what, let me go ahead and do the algebra, it's not a problem. It's going to be b tilde times j plus 1 times j plus 1 minus b tilde times j plus 1. Now, after a little bit of algebra, what we end up with is a new observed equal to 2b times j plus 1. And again, we know this already, not a problem. J equals 0, 1, 2. J is the initial rotational state.